Okay, it's the physics formalism Helmholtz matrix to column gauge. That's the idea is that everything right now is derived from set theory and things like that, and also there's one from quantum physics and another from relativistic physics, the photons and everything. But I thought we go back and start at the point level itself. So you can imagine the whole universe to be a matrix of points. So what happens at the point? That's what we are looking at. So I derived a matrix for the point field itself. People have done that before for 0 point field. From Sakharov, other people, they have actually reduced everything to a point. But what happens to the point is that there are two types of fields. One is and I will show that briefly. Again, I'm showing only the highlights here. So mainly, see, you have the two fields, rotational field and a gradient field. So gradient field is where the rotational, at 0 point, this rotational field will be absent. There will be no vortexes. So rotational field represents vortex action. Whereas gradient field simply says that there's a field, a gradient, a field that is emanating out. Either is converging or diverging. For example, in a North Pole or South Pole, you have a field. North Pole, it's diverging. The field is going away from it. It's like a source. The South Pole, it is converging. So it's like a sink. So that's the gradient field. So this is all that's happening at the 0 point field. But in a micro black hole, I reduce the black holes as a sink. So point field will act like a source, and the micro black hole will act like a sink. So there is only a rotational field or a vortex field. So every point can be either either a source or a sink. So one point may be a source, another point may be a sink, so that the whole circuit of the flow will occur. For example, this is the idea of a star. Star is like, a source which is radiating out, and planet and other things are sinks or a black hole that will absorb that. So same thing happens at the point. So a point can be either one. So this is the idea from I.M. Hercules and the paper I cited here. Rajane I.M. Hercules, Theory of Superluminous Vacuum Quanta. It's published peer-reviewed publication, Physics and Astronomy International Journal. And this is in this year. So earlier this year, it was there in June. So that is that's the paper that shows the formalism. So I'm not going to go over the details of that right now for the sake of thing. And if I pull up that, if you pull up this, you can briefly see that. I know it's blocked. Okay. No, okay. So mainly, right. So let me go back here. So that is the basis. That's the basis on which all the rest is built upon. So you have the Helmholtz. It's called the Helmholtz decomposition of the fields, which means that there's a gradient field and a vortex field. That's all Helmholtz is saying. So that's very fundamental. I believe that it's probably more fundamental than Maxwell formulation, but people may question on that. But and I have also derived a Maxwell equation for monopoles and things like that, corrected Maxwell equation. So I think you have to look at the whole field theory in a totally different light. But the Helmholtz seems to give a more fundamental depiction of how the fields act. So you have then the first formalism. I call it Mark Wallach's formalism. that gives this matrix or matrix of rotational field and gradient field. That's all. And now I gauge it. I gauge that field in terms of energy, because now we are to at 0 point we find that it's actually energy. It's like a 0 point field energy. That's how the formulation worked. Again, that is a partial differential equation. When I derive from the eigen matrix, you can finally get the equation of motion in terms of the energy. So the partial differential equation shows that at the 0 point it should be the energy. So I had to gauge it to the energy. Yeah, this is the second page actually.
Okay.
So the first page I showed, again I repeat that. So the first page is a physics formalism. That's the title, matrix to Coulomb gauge. So I'm gauging from Helmholtz matrix, which is the fundamental formalism, to a Coulomb gauge. So we can gauge it step by step to the level we need, all the way to gravitation. So this is the idea, and I'm presenting it this is for a presentation, formal presentation for 6th International Conference on Combinatronics, Cryptography, Computer Science, and Computation this month, November 17th to 18th. Okay, so the abstract says, so I give briefly introduction there, but the abstract says hierarchical Helmholtz Hamiltonian matrix have been gauged to Coulombic Hilbert matrix representing Gilbertian and Amberian nature. So Gilbertian and Amberian essentially means electromagnetic fields in terms of electric field and magnetic field. Mechanics of vortex rotational fields acting with gradient field. So that's what basically it is. As a point, you have both the gradient field and the vortex field. So it's 0 point micro-backward general field. So any point can be either 0 point or a micro-backward. Means 0 point means it's emitting or it's a source. Micro-backward means it's a sink or it's absorbing the field. So 0 point essentially will be a divergent field. With micro-backward, it will be a convergent field. Extensive vacuum electromagnetic gravitational field gauge. Okay, so when I solve for the vacuum gravitation solution, I can get these type of matrix where it shows the Hilbert, the Coulombic Hilbert gauge, and the inverse of that. Okay, and it has a negative sign here. And then you have in vacuum, this is 0, this mass. And then you have a mass that shows for the Hilbert gauge. Okay, so we can extend this because I will show in the continuing presentation, I can convert to a unitary matrix and I can substitute for this value here, negative G inverse, and I keep substituting it. I can extend this matrix all the way to infinity. So that will give me like a string matrix that shows charge asymmetry gauge matrix. So okay, so the gauge transfers are necessary part of physics. We know that gauge is very important, so that the gauge tries to bring all other theories together. That may be one of the solutions to cope up with the differing aspect of quantum nature and the relativistic nature, the supersymmetry, the string theory, and everything. Everything has to be put on one gauge platform so that we can compare them and understand what's going on. Even classical physics, Maxwell, everything is gauged now. Einstein theory and also the Schrodinger equation, everything is gauged now. But we have to be very careful how we gauge that. So I'm going through some of the steps here. That's the idea. Okay, so configuring this, the hierarchical Helmholtz Hamiltonian, which is this matrix, simplified matrix, to the Amberian Gilbert Coulombic matrix. So the whole thing is called Amberian. So this is the first step. This is not the Amberian Coulomb matrix gauge, but this is the first step. And as I mentioned, the field, tensor field, E tensor, subscript G mu V is the point gradient converging field, and that's gauged to the energy point converging field E sub G. So very simply, this field is gauged to this energy, and you see that field. I like to describe field as a second space derivative of the energy. Okay. So the tensor field with the superscript mu v shows it's a diverging field, and similarly the tensor field subscript r mu v is the rotational point vortex converging field. So it's essentially a vortex field, but it's a converging field of vortex. So you have both converging and diverging fields. So it takes into account both aspects. And the tensor field, the subscript r and superscript mu v shows the rotational vortex diverging field. So these are symbols that will help in distinguishing. Mathematically, also we can move forward with that. So essentially, we have gauge to the energy and the field. Now we can gauge that energy and the field to the Coulomb gauge as well as the Hilbert gauge. So this del square Eg will be gauges to Coulomb gauge. So that is the G subscript G superscript mu v, and the one for the point field energy, 0 point field energy, gauges to the Coulomb gauge with the subscript mu v. Okay, and now the rotational field will gauge to the Higgs field to describe the Higgs boson mass, things like that eventually. So this is a mass gauge, MR, M subscript R mu V, M subscript superscript mu V. They are the mass metrics for the Higgs. So essentially we are done now. Helmholtz metrics to Coulomb gauge. Okay, so the vacuum gravitational fields, then I can say this the mass gauge here goes to 0, and there is one mass that's remaining, and it's very important. Again, I need more discussion why this mass is described, but it describes why the vacuum is not empty. It will automatically describe that. But I derived that not using that fact, but something else. Again, it needs more description. So I don't want to spend too much time on it, but it leaves behind a mass matrix. But eventually, surprisingly, that will describe why the vacuum is not empty. It's actually, it has some particles, something in there always. Okay, so in the case of the Coulomb gauge, you have the upper subscript is G, the lower subscript becomes inverse of that. Again, I derived that based on certain conjectures, and we eventually had to prove it with the observable, no question about that. But mathematically, logically, it makes sense to do this. And so you have the gauge of Coulomb gauge and the gauge inverter of inverse Coulomb gauge as well. Okay, so the idea is that the vortex up, the vortex down is the inverse of that. So it's almost like a mirror image of that. So M's are again, you can describe eventually dark matter energy. Again, these are questionable now, dark matter, whether it is true or not exists. But if it exists like that, then that will describe the dark matter as well. So the idea is that in the vacuum, you have 0, and then you have the dark matter energy, the flavor, that M remains there. So something remains in the vacuum. Even, there is an absolute 0 vacuum. So there's something in there. Okay, So when I find the determinant of this matrix, simply by simple multiplication of the diagonal terms or the cost diagonal terms and subtract that, the usual determinant finding for the matrix, I get a magnitude of -1 or negative I, which is the identity matrix, -1. Okay, so when I correct that, when I put that value in, then I get the corrected matrix as 0, m, and minus g inverse 1 and g. So it's a very simple matrix, simplified matrix now. But this -1 has a lot of importance because I can make into unitary instead of I, and then I can say this one by saying that this matrix, I'm not getting rid of the negative sign or anything, but I'm saying this one will represent mirror symmetry of G inverse. Now, okay, so the point matrix reflection imaginary parity value. So it's I, essentially, when you multiply, you get I. So the imaginary value actually comes into picture, but I don't want to complicate this one using those. I just want to move on to the string matrix that I was talking about. So the negative I helps me to actually extend by using unitary matrix. I can extend this matrix all the way to infinity in this way. So I substitute the value of the negative I, the negative value, and I can keep increasing the matrix. So you see that there is an asymmetry automatically, gauge matrix. So there is an asymmetry here. But this side will, so you can represent positron electrons as well as the North Pole, South Pole. So it can apply to our Helmholtz Pauli-Dirac Planck circuitry that we are talking about. Okay. So the G inverse to G, the cost diagonal will extend like gauge ray analogous to negative charge like fermion or electron of Gilbertian nature, for infinity bringing to real space like volt. So it describes, eventually we can use that eventually to actually define how we are finding the volt or potential, because the volt is defined as an electron taken from infinity to the reference 0. So that's how a volt, the definition of a volt of a potential. So that's a classical definition of potential unit volt. So we can actually derive from this analytics that aspect. So that partially says that it gauges to the classical definitions to some degree. So therefore, G inverse to G will represent Coulomb gauge fermion charge of micro. So this aspect can, this cross diagonal then can represent a fermion. I'm also going to use one more proof formalism that I published with the manual. Physics, biophysics. Again, that's a very, very fundamental mathematics thing. I can present probably in further meetings as well as in the general conference. Again, that's a very fundamental matrix based on matrix properties only. I'm not going, but I'm going to use the results of that. So I can use a functional, describe a functional from that in terms of a functional f of t, f subscript t superscript e, I call that functional, in terms of the quantum density matrix rho of t, and then wave function of converging field, wave function of the diverging field. So that is your inner product, the inner and outer products aspects we use this here. And you have to invert that times scalar potential. So V is a scalar potential. And the scalar potential is a general energy field like a scalar potential in general relativity. I should close the bracket here. Okay. So substituting equivalent gauge parameters as del square of the energy, the diverging energy, as the Coulomb gauge, like we did before. So then the functional is essentially a Coulomb gauge. Then I can use also y, the normal definition of y equal to f of x, where x equal to the quantum density matrix rho of t, and y is f of the functional. So then I can use the scalar potential in terms of the energy, and it's a derivative, the space derivative of energy. So based on that, the scalar potential, how the scalar potential works with the quantum density. So a lot of descriptions are there. I'm not going to go into details about that. It's a lot of things we can get out of it in terms of quantum. So it relates the scalar potential to quantum density matrix, and all this brings together. So it can represent a coupling constant for like a coupling constant for general relativity. So I can essentially write this Coulomb gauge in terms of the so the f of Eg substitute as a Coulomb gauge, and then I can substitute these values, the scalar potential in terms of energy, and the quantum density matrix. Essentially, it's a substitution of these variables, and then I can write a function transforming my chromat as rho of t to g. Like I said, y equal to f of x. So then I can write f in this case is the whole thing. I put it as f factor f, and then g is f times the matrix, the quantum density matrix. So now I connect the Coulomb gauge to the quantum density matrix, which is the fundamental thing that people are relating, how the density matrix affects the gauge, or the gauge affects the density matrix, and that describes how the particle is formed, how waves are formed, how everything you can relate that in abstract sense. So we can apply these fundamental formalism to understanding the quantum nature of particle and wave. So we can see what happens. So what it means that it describes that it can only work in certain way. This is what we are restricting, and also functional. We are going to use that later on. Functors, like I described before, functors are different categories. Like you have one particle, another particle. They are like functors, and this functional, which depends on the time, the quantum density matrix, which depends on the time, is going to connect them. And I have derived now gravity goes one way and the time goes the other way as a functional. So they can connect or disconnect each other. So the particles, that's why the particles can be discrete, but also they can bring it together. And that describes also quantum entanglement on quantum decoherence aspect. And
okay, thanks, Rajan. That was very interesting.
Thank you.
So I suppose the first question is why is the Higgs mass matrix associated with rotation? Because the Higgs mass is sitting on the real diagonal,
yeah,
and that means it's a rotation. It's part of the rotation, yeah.
Yes.
So why do you equate the two, or?
Yes, I believe that mainly the mass aspects comes because of the vortex nature. They actually, you can think of everything as a wave to start with, but when it starts rotating, because our PDP circuitry also shows eventually that it has to rotate. There's a clockwork that's going on. So there is a rotational field, and it's obvious from the Helmholtz field also. That rotational field is the one that is concentrating. I think of the matter as a condensed wave, a condensed wave. So the rotation, when the vortex field goes and it starts what you call a densification process, kind of a condensation or densification process. So highly densified wave becomes the mass.
Yeah.
Your vortex field, is that a cyclone type of thing?
It could be think of as a very simple analogy, yes. To see a picture, a simple picture, in water, for example, in water we have vortex fields, right? Vortices that's happening.
Well, in water, there's also these ring vortexes.
Yes.
like smoke rings. Is that
Yes.
part of your math too?
Yes, this is a more general, but specific aspects are the smoke rings will be part of that. They are all part of the, but I think it's all subset of the vortex fields. Very specific
So you do
subset.
include rings.
Okay, well, yeah, you were talking about gravity going one way and time going the other. Like, if we think of gravity, it's kind of a negative field. It's always like pointing in one direction. And time, therefore, is also another unidirectional flow. So would you say that they are moving in opposite directions spatially? Is that why you would have them going in the opposite direction?
Yeah, actually, I derived that. There is a derivation. I have shown a picture. I'll show later on. But let me see whether I can pull up that or not. But
what is that? What is that?
Yeah, that's an earlier one. That's an earlier one.
Cool. Yeah.
Yeah. See, this one here, it shows the connection, how the time is connected in a way, So it shows that time is connected. Yeah, that's one way you can see that. Yes.
Cool.
Yeah, that's our original. Yeah, that's a theory of the superluminous quanta that we talked about.
Right.
Thank you. Thank you for John for showing that.